Use 5 here in the Johansen test, we got a near singular matrix. And then we used 4. However, keep in mind that something that I forgot. The Johansen test takes into account lag intervals in first differences. So given that we identified the lag order equal to 5, we must put here the first difference lag order, which is minus 1. So 5 minus 1 equal to 4.
So that it was 5 minus.
Yeah, it was fine. Okay? So whatever lag order you get from the lag structure, put minus 1 in the Johansen's test, because it takes into account lags in first differences. Okay, so what is our evidence now? We have 3 co-integrating orders and 4 lags in first differences. So we go to estimate, go to a vector error correction model, leave the endogenous variables as they are, because keep in mind, the vector error correction model automatically applies +1 order of difference. So meaning that if we have our variables here at levels, we are going to get variables in first differences. The lag interval changes from 2 to 4. And also, let's stick to the strict case over here. We have a number of co-integrating relationships. Number of co-integrating relationships equal to 3. Meaning that we have 3 equilibrium points. If you do that, click OK. And this is what you get. Here we have the 3 co-integrating relationships. However, as you can see, GDP consumption and investment are treated as the dependent variables in all of those co-integrating equations. And in order to identify which variable is the dependent variable, have a look at this one. Given that this value here is 1, GDP is the dependent variable in this equilibrium point. In this case, consumption is the dependent variable in that equilibrium point. In this case, it's investment, and so on. Meaning that, as the model stands right now, we can test for long-run relationship between expenditure and current account balance on GDP, consumption, and investment. Can we test the relationship, the long-run relationship, between consumption and GDP? The answer is no. Investment and GDP? The answer is once again no. So what happens if we want to test that relationship? The answer is we change the number of integrations. Again, we just leave 1. However, as the model stands right now, we have 3 equilibrium points, 3 long-run relationships. So the next question is that, are those long-run relationships significant? We always have a look here at the number in the bracket and compare it with what? With the critical value of the t-statistic at the 5% point of significance, which is equal to 1.96. Now, keep in mind that we take into account the absolute value in the brackets and compare it to 1.96. If it is above 1.96, then we accept this estimation, this coefficient over here. If it's below 1.96, we reject it, so it's equal to 0. Because always keep in mind, the null hypothesis of a coefficient is that it's equal to 0 versus the alternative that it's equal to this number over here.
Sorry, are you talking about the on expenditure, the minus 1.15, if that's above 1.96 or below? Over there, expenditure.
This one.
Oh, that.
Okay, as you can see, well, the t-statistics are in brackets.
Yeah.
Okay, so it's the t-statistic values that we take into account, that we compare to 1.96. Yes?
Would you say if you reject the coefficient is 0?
Always keep in mind that The null hypothesis of those coefficients over here is that the coefficient is 0, and that happens when the t-statistic is below 1.96. But if it's above 1.96, we get this value over here. So we reject the null hypothesis that the coefficient is 0, and we accept this one over here. So expenditure here is significant. Current account balance is significant on GDP, but expenditure is insignificant on consumption. Current account balance is significant on consumption, and both of those here are significant on investment. So the only significant long-run estimation is expenditure on consumption. Okay, because it's minus 1.47, which in absolute value is below 1.96. Meaning that we identified 3 equilibrium points. However, how do we know if our model converges back to those equilibrium points? 2 conditions must be met. Those coefficients here, the co-integrating coefficients, must be equal, no, actually they must range between 0 and minus 1, where 0 denotes total rigidity to a short run point, and minus 1 total flexibility back to equilibrium. So let's start with this case. The speed of adjustment of the first co-integrating equation. It's minus 0.28. However, the t-statistic is minus 0.48, way below 1.96. So what do we do here? We accept the null hypothesis that the speed of adjustment is equal to 0 and not equal to minus 0.28. If the speed of adjustment is equal to 0, what does this mean for our model? Convergence back to equilibrium, divergence, or something else? If we get the speed of adjustment equal to 0, what does this mean for our model? Does it converge back to equilibrium, diverges from equilibrium, or something else?
Total rigidity.
It's total rigidity, absolutely nothing. It's stuck at a particular short-run point, which is not the long-run equilibrium. Okay, for instance, if you test this one, the co-integrating, the speed of price adjustment of this equation over here. Actually, it's the speed of consumption adjustment. The value is 0.07, but it's insignificant as well. So once again, we have total rigidity. Thus, we can see the third coefficient as well. The third speed of adjustment is once again insignificant. Meaning that our model, as it stands right now, has 2 equilibrium points, but it does not converge to any of those points. So our model is stuck to a short-run point. Yes?
Do we not look at the t-statistics for the consumption, investment, expenditure?
Yes, you could do that as well, but I would recommend to stick only to this one, to DGDP, because this equation is of our interest.
So should we not mention cons and investment?
No, you are going, however, to need these estimations over here for the Granger causality test. However, given that it's automatically calculated, just mention the final joint statistics. Okay, you won't have to take them into account directly.
Okay. So like all those values for consumption, investment, expenditure, they automatically go for greater. Alright.
Yes. So what's the first step here of the vector error correction model? We identified 3 equilibrium points, but there is no convergence to the equilibrium points. So the next step that we have to take into account is short-run effects. If there is causality between 2 variables. So what do we do? Given that we identify long-run equilibrium, but total rigidity to a short-run point, then we have to see what happens to that point. So we go to lag structure, greater causality block exogeneity tests, and click on OK. As you can see, we have 5 equations where each variable is treated as the dependent variable, and we try to see whether the independent variables cause the dependent variable. In other words, if a change in the independent variables here will cause a change in the dependent variable. So what do we want to see? The null hypothesis of Granger causality test is that there is no causality running from the independent to the dependent variable, versus the alternative that there is causality running from the independent to the dependent variable. Now let's see, is causality running from consumption to GDP? Yes or no? No. Why is that? Because probability is 0.58. Meaning that we accept the null hypothesis that there is no causation, no Granger causality. Investment. The probability is 0.72. Is Granger causality running from investment to GDP? The answer is no. Once again, because it's above 0.05. The same for expenditure, because it's equal to 0.07. But the probability of current account balance, once again, yes, I thought it was 1.01. So it's 0.16. Once again, it's insignificant. So what is the main outcome here? For our model, none of those variables appear to have significant effect on GDP. Always assuming that the lag order is equal to 4 and the number of co-integrating relationships is equal to 3. Now, if you're going to read the following tables, you're going to provide an interpretation to those results. For instance, as you can see here, expenditure, only expenditure is affecting consumption, meaning that if there is a change in expenditure, consumption is going to change as well. Okay, that's the main effect. So, fiscal policies will affect the level of consumption. That could be an interpretation of this result. Okay, and if you see the following tables, whenever you see a significant probability here, below 0.05, you can argue that there is causality running from the independent to the dependent variable. Any questions up to this point? These are the 2 steps that you have to follow if you estimate a vector error correction model. Identify what happens with long-run equilibrium, long-run relationship, and the speed of adjustment to that equilibrium, and run the Granger causality test.
You know, when we are interpreting every single one of them, should we include every single table?
You could form a table that is going to have on the horizontal axis 5 variables, then 5 variables on the vertical axis, and then you can put the values there. So you will have a 5 times 5 table. Any questions on those steps over here? So what is the main flaw of this analysis so far? The answer is we run an error correction model without identifying whether the lag structure results in not serially correlated residual terms. So if we go to estimation output, before doing all that, we have to go to View, lag structure, no, residual test, and autocorrelation LM test. Click on this one, put lag order equal to 10, and then click OK. Do we have any residual terms that are autocorrelated? The answer is yes. Number 3, number 4, and number 8. Meaning that our results may be unbiased, but they are inefficient. So the Akaike information criteria test do not provide a lag structure that is not subject to serial correlation. So what do we do? What is the next step? The answer is try to find that lag order for which there is no serial correlation. What I would do in this case? First of all, I would include a number of cointegrating relationships equal to 1. And why is that? Because I want to find a long-run relationship between consumption and GDP, and in particular, all of the independent variables and GDP. So whatever the indications of the Johansen test, if there is indication of at least one cointegrating order, I would include one cointegrating order. That's the first thing that I would do. So by doing that, click OK, and once again go to residual test, autocorrelation LM test, include 10 lags, and see whether we have serial correlation. Now, as you can see, serial correlation is restricted to number 8. So we want to remove this as well. What do we do now? Change the lag order. I would change it from 4, let's say, to 2. And click OK with one cointegrating relationship. Go to View, Residual Tests, Autocorrelation, put 10, and click OK. What happens now? Insignificant results, all of them. So there is no serial correlation. So a lag order equal to 2 in first differences results in non-serially correlated residual terms in the vector error correction model. So after the identification of the absence of serial correlation, then go once again to View, Residual Tests, and go to white heteroscedasticity with no cross terms. If you click on this one, you will see that we got a probability that is significant, meaning that there is heteroscedasticity in the error, in the residual term. So what do we do in this case? Keep in mind that at this stage, all that we want to identify is the absence of serial correlation. If you have heteroscedasticity, leave it there. Mention that there is, but leave it as it is. Okay, there are ways to correct heteroscedasticity, like the weighted least squares or the generalized least squares, which we are going to discuss when we come back from Easter break. This is not going to be material for your report. Okay, because it's rather complicated so far.
So do we do this, the residual test and this heteroscedasticity test before we do the Granger causality?
Exactly. Before you run the Granger causality test and identify whether there is long-run equilibrium or not. Do that before.
So wait, what, before the co-integration? Or?
No, after the co-integration.
So just before the Granger causality?
Exactly.
Okay.
So right now, let's have a model where this is the long-run equilibrium relationship. The effect of consumption on GDP is significant, and always keep in mind that those signs here are the opposite in the long-run relationship. This means that there is a positive effect of consumption on GDP. If consumption goes up by £1, then GDP is going to go up by 1.17, not down. Okay, so always remember that the signs that we get in the long run relationship is always the opposite from the one of the main interpretation. So all of those effects there are positive, and also they are significant because the t-statistics in absolute terms are way above 1.96. So there is a long-run equilibrium expressed by that relationship over here, over there. So the next question is, what is the speed of adjustment? The speed of adjustment is indicated by this coefficient over here. It's minus 0.21. However, given that the t-statistic is insignificant, we reject that value, the value of 0.21. And we accept that the speed of adjustment is 0. Meaning that our model does not converge back to that equilibrium over here when the lag order is equal to 2. Meaning that there are only short-run effects. So, the next step is to estimate Granger causality. Okay, and if you do that, provide the interpretation of your results, and you're done with the error correction model.
If it shows that it never converges to the long run, does that mean we have to run the bar?
No. You don't have to run the VAR at this stage. All that you have to do is run causality test, provide interpretation of the short-run coefficients. Any questions about the error correction model? Okay, now, assume that we got insignificant results by the cointegration test, meaning that there is no cointegrating relationship among our variables, so we can't estimate a vector error correction model, and instead we have to estimate a VAR. Keep in mind, always keep in mind that whenever you estimate a VAR, the variables that you use here are going to be reflected in the VAR. So, if you leave variables at levels, the VAR is going to take those variables into account. However, a VAR like that will be non-stationary, meaning that our results are going to be incorrect. So what do we have to do? Given that all of those variables are integrated at first order, use the first differences. So convert it to dGDP, the consumption, the investment, the expenditure, and the current account balance. If you do that and click on VAR, those variables are going to be taken into account. So press enter. And here you're going to get those results. The first thing that you do, once again, is go to view, residual test, and autocorrelation LM test. Put a number of lags equal to 10, and see whether there is serial correlation or not. As you can see, in our VAR here, there exists serial correlation. So what do? Change the lag order. Let's say from 2 to 4. And click OK. If you do that, once again go to View, Residual Tests, Autocorrelation LM Test, lags to include 10, and press OK. As you can see, once again, we have serial correlation in 1, 2, 3, 4, 5. Okay, that's way too significant. Estimate. Use 3 lags. Press enter. Residual tests. Autocorrelation. 10 lags. And do the same. What happened with 3 lags? So only the last one is significant. So now we run out of lags. If you run out of lags and you can't find a lag order for which there is no serial correlation, what do? The first option would be that choose that lag order for which you minimize the number of lags with serial correlation. So in our case, we pick this one. Or this means there's something wrong with your co-integration test. Why do we get serially correlated error terms here? The answer is because there is co-integration. There exists co-integration between our variables, and yet we estimated a var. Okay, so we have evidence that we should go for an error correction model, but we estimated a var. So this is why, in this particular case, that we have serial correlation. If Johansen's test was insignificant, okay, so no asterisks at all, we wouldn't have serial correlation here. Okay, so for the time being, assume that we choose that lag order for which the number of lags that are serially correlated is minimized. So go to estimate and click OK. You have all these values over here. Do you have to reflect them in table? The answer is no. What do? First step in var, Granger causality test. The procedure is exactly the same. Go to view, lag structure, Granger causality block exogeneity test. And you are going to get the same tables and provide the interpretation in order to see whether causality is running from one model, from one variable to another. This is the first step, exactly as we did before. So for instance, in this case, no causality running from any variables to GDP. No causality running here from any variable to consumption. The same for investment. Expenditure is affected by all of those variables because it's below 0.05. Well, except actually from consumption. Consumption does not cause expenditure. And current account balance is only affected by expenditure because the probability, no, actually by both GDP and expenditure, because probabilities are below 5%. Okay, so you have to give an interpretation according to whether there is causality running from the independent variables to the dependent variable. This is the first thing that you have to do in var. The second thing is